Noche Cósmica.
There exists one question that planetary scientists rarely ask aloud, not because it lacks importance, but because the answer troubles something deep in our certainty about the cosmos. If Jupiter, that enormous guardian of the solar system, were to simply vanish tomorrow, what would actually become of us? The question sounds almost theatrical, doesn't it? Impossible and philosophical at once. Yet buried within this seemingly fantastical scenario lies real science, genuine physics, actual orbital mechanics, and mechanisms of planetary protection that most of us have never fully considered, even though our existence hinges upon them. For most of human history, we didn't even know Jupiter was there. We saw it as a wandering star, bright and peculiar, moving in ways that defied the fixed order of the heavens. It wasn't until Galileo turned his telescope skyward in 1610 that we discovered those 4 large moons orbiting it. And in that single moment, everything we thought we understood about the center of the universe began to shift. But knowing that Jupiter exists and understanding what Jupiter actually does are 2 entirely different things. Even now, with spacecraft that have crossed billions of miles and instruments sensitive enough to detect the heat of distant exoplanets, we're still uncovering the true scope of Jupiter's influence. And that's where our question becomes not just intriguing, but genuinely unsettling. Consider what astronomers have learned over the last few decades, particularly from studying other star systems and from careful analysis of the meteorite craters that scar our own world. Jupiter isn't simply a massive planet hanging in space. It's an active participant in the architecture of the solar system. It pulls, it pushes, it shields, it clears. Its gravitational presence has shaped where asteroids can orbit, which comets venture inward, and ultimately, where life-bearing planets remain stable enough for biology to take root and flourish. What happens if that presence simply ceases? The implications unravel outward in ways that touch everything from the stability of Earth's orbit to the frequency of catastrophic impacts to the very long-term viability of conditions that allowed us to exist in the first place. This isn't a documentary about apocalyptic fantasy, though there's certainly an element of drama to follow. Rather, it's an invitation to understand one of the solar system's most profound dependencies, and to recognize that the cosmos we inhabit is far more intricately balanced than we typically give it credit for. By walking through this thought experiment, by imagining what would unravel if the great planet vanished, we're going to come to understand Jupiter itself far more deeply than we could by simply observing it as it is. We'll trace the invisible threads that bind our world to its gravity, and we'll see why Jupiter's existence represents something close to a cosmic miracle for anything hoping to live on a rocky planet like Earth. If you find yourself drawn to questions about what lies hidden in the mechanisms of our solar system, about the fragile equilibrium that makes life possible, about the kinds of cosmic forces that operate beyond our everyday perception, then consider subscribing to explore more scenarios where we examine the hidden dependencies of our world. These thought experiments can offer profound insight into how our universe actually works, and that knowledge tends to settle into the deepest part of our understanding, especially when explored in quiet moments like these. Now, let's begin by stepping back, metaphorically, and asking ourselves what Jupiter actually is. Not what it looks like through a telescope, not its famous red spot or its rapid rotation, but what it fundamentally is in terms of mass and gravitational influence. The number itself is almost too large to hold in the mind comfortably. Jupiter contains more than twice the mass of all other planets in the solar system combined. If you gathered up Mercury, Venus, Earth, Mars, Saturn, Uranus, and Neptune, added them all together, Jupiter would still outweigh them. It's not simply a large planet. It's something closer to a failed star, a massive sphere of hydrogen and helium that came tantalizingly close to achieving the internal pressure and temperature necessary for nuclear fusion, but stopped just short. In another possible universe, with slightly different initial conditions, Jupiter might have ignited, and our solar system would have been a binary star system instead. But in our universe, Jupiter is exactly what it is, gravitationally vast, but just massive enough to remain dark, to remain a planet, and in that precise state, to be capable of profoundly shaping the world around it. Think about gravitational influence not as something abstract, but as a presence. Everywhere Jupiter orbits, its gravity creates a kind of highway and barrier system. Asteroids and comets moving through space don't simply pass by each other randomly. They're drawn by gravity, deflected by gravity, accelerated or decelerated. Jupiter, with its immense mass, becomes one of the dominant forces shaping which objects follow which paths. And for hundreds of millions of years, as the solar system has evolved and settled into its current configuration, Jupiter's presence has been sculpting trajectories, clearing zones, and establishing boundaries. Remove that sculptor, and the entire composition changes. The Earth itself, this world we inhabit, exists in a region of space that was once far more crowded and chaotic than it is now. In the earliest history of our solar system, about 4.6 billion years ago, the planets were forming in a disk of dust and gas. Gravity was pulling these particles together, creating bodies of increasing size, and at the same time, gravitational interactions between these growing bodies were constantly shifting their positions. It was a slow-motion collision zone, in a sense. Things were falling together, merging, clearing orbital paths. And through all of this turbulence, Jupiter was already present and already massive, already exerting tremendous influence. Some of the earliest research into these dynamics suggested that without Jupiter, Earth might have accreted far more massive, pulling in many more planetesimals and asteroids before its orbit stabilized. We might have become a much larger, much hotter world, quite different from the one that eventually allowed life to begin. There's a particular irony in how long it took for planetary science to recognize this. For decades, astronomers studying the formation of planetary systems elsewhere in the galaxy noticed something curious. Many of those distant systems seem to have what we call hot Jupiters, enormous planets orbiting very close to their parent stars, close enough that their surfaces would be torched by radiation. These seemed to be the norm, not the exception. It was strange. Our own solar system, with its smaller inner planets and its massive gas giants in the outer reaches, began to seem unusual, perhaps even rare. And the question naturally arose, why is our arrangement so different? What made our system develop the way it did, rather than this apparently common pattern? The answer, as it turned out, involves migration, catastrophic rearrangement, and Jupiter moving dramatically from where it was born, potentially even passing closer to the inner solar system before settling back into its current orbit, in what's known as the Grand Tack hypothesis. The details of this ancient history are still being researched and debated, but what matters for our thought experiment is this: Jupiter's position, Jupiter's mass, Jupiter's current orbit were not accidental. They were the result of billions of years of gravitational dynamics, and they've ended up exactly where they need to be for planets like Earth to exist in habitable zones around their stars. So when we ask what would happen if Jupiter disappeared, we're really asking what would happen if that masterwork of gravitational architecture were suddenly erased. The answer requires us to think deeply about the mechanisms by which Jupiter has maintained the stability of the inner solar system for the last few billion years, and to imagine what would occur if those mechanisms simply switched off. What would happen to the asteroids that Jupiter shepherds? What would change about the cometary impacts that strike Earth? How would the orbits of the inner planets themselves, long settled into their current configurations, begin to drift and shift? These are the questions we'll be exploring as we move deeper into this scenario, allowing ourselves to imagine a world where Jupiter's invisible hand no longer steadies the gravitational dance of the solar system. In the darkness of this thought experiment lies something worth understanding deeply: just how much we owe to the presence of a planet we rarely think about, orbiting far beyond our sky. The loss of Jupiter would unfold across what we might call seasons of catastrophe, though the first and most immediate would be almost invisible to anyone standing on Earth. For several hours, perhaps even a full day, most of humanity would notice nothing at all. Jupiter would not simply vanish like a light switch. Such a scenario invites us instead to imagine a sudden departure, perhaps a kind of instantaneous removal, and in that removal, the first consequence would be gravitational silence in the space where the great planet once orbited. You see, Jupiter has been pulling on our solar system since before Earth even cooled from its molten beginning. It orbits at a distance that seems almost casually far away, some 500 million miles from the Sun on average. Yet its gravitational embrace extends far beyond its own orbit in subtle, persistent ways. The asteroids between Mars and Jupiter have been held in their scattered arrangement, in part by Jupiter's enormous mass. And while we might imagine that such distant rocks would hardly care about the absence of a planet, what we forget is that gravity works in both directions. The asteroids have been held in a kind of stable dance with Jupiter for the entire history of the solar system, and that dance partner, suddenly, would simply not be there. The transformation would begin almost immediately in that belt of rubble and stone. Asteroids that had been traveling in their established paths, influenced by the gravitational tugging of a body more massive than anything else in their vicinity, would suddenly find themselves set free. Without Jupiter's constant herding influence, their orbital paths would begin to drift. Some would be pushed closer to the Sun, others would wander farther from it. It is perhaps useful to imagine a crowded marketplace where a large figure has been standing, creating an invisible shelter and directing traffic around them, and then that figure simply walks away. The crowd would no longer have that invisible boundary. Movement would become less predictable, more chaotic. This redistribution would take time, of course. We are not speaking of immediate collisions or rapid restructuring, but over decades and centuries, the asteroid belt would transform. Asteroids would begin to drift in new directions, sometimes colliding with one another as their paths crossed in ways they never had before. Some would be ejected from the solar system entirely, sent careening off into the darkness of interstellar space. Others would fall inward, drawn by the Sun's gravity into new orbits that would eventually bring them into the warmer, inner reaches of the solar system. Here is where the true significance begins to make itself clear. Our own solar system, the one we inhabit, exists in a state of relative stability, partly because of Jupiter. The great planet has, for billions of years, acted as what astronomers sometimes call a gravitational shield, or, in other framings, a cosmic janitor. As objects have drifted in from the outer regions of the system, Jupiter's presence has either deflected them, captured them as moons, or drawn them inward, where they would collide with the Sun. In some cases, Jupiter has done something else. It has captured asteroids and small bodies into the Lagrange points, those peculiar zones where gravitational forces balance in such a way that objects can remain relatively still with respect to both Jupiter and the Sun. Without Jupiter, those protective roles would fall away. And so we might ask, what happens to all of those asteroids that have been, in a sense, herded away from the inner solar system for all these billions of years? The answer unfolds slowly at first, then with increasing urgency. The asteroid belt, now shepherded only by the Sun and by the mutual gravitational interactions of its own members, would become far more chaotic. Collision rates would increase. Some asteroids would, within a few 100,000 years, a mere blink in cosmic time, begin to drift inward. Their new orbits would carry them closer to the Sun with each pass, and closer still, until eventually some of them would find themselves on trajectories that intersected with the orbital paths of planets that still remained: Mars, Earth, Venus, Mercury. We are speaking now of a solar system where impacts would become not a rare event, but a recurring crisis, where the sky above Earth would eventually begin to bear fresh scars from impacts that occur not once every 100 million years, but perhaps several times in 1,000,000 years, or more frequently still. The warming mathematics of that thought, the simple calculation of how much more often a disaster becomes simply by changing one factor, is something worth holding gently in your mind as we move deeper into this scenario. Jupiter's absence would rewrite the safety margins that have allowed life on Earth to persist and flourish. It would be like removing the walls from a room and wondering what would happen to the people inside as the weather moved in. The asteroid belt itself would remain, for now, drifting in its ancient patterns between Mars and where Jupiter once orbited. But without that great gravitational shepherd, those rocky bodies would begin a slow, irreversible journey, outward and inward both, pulled by the Sun's steady hand and by one another in intricate gravitational dances that would play out over millions of years. Picture, if you will, the inner solar system as it exists today, a kind of celestial equilibrium, a balance maintained not by accident, but by Jupiter's commanding presence. That balance, once disturbed, would unravel with a kind of terrible grace. The most immediate, and perhaps most profound consequence, would touch the very world beneath our feet. Earth's orbit, stable for billions of years, would begin to shift. Not dramatically, not overnight, but over centuries and millennia. Our planet's path around the Sun would become increasingly elliptical. The seasons that have governed our civilizations, the monsoons that feed billions, the winters that shaped human migration, the summers that ripened our harvests, would grow more extreme. Some scientists suggest that without Jupiter's gravitational anchor in the outer system, Earth could eventually venture into a region of space significantly warmer or colder than it is today. The climate feedback loops that currently define our biosphere would accelerate and destabilize. But there is something even more unsettling to consider, something that happened in the ancient past and would certainly happen again. The inner planets, Mercury, Venus, Earth, and Mars, would gradually migrate. Mars, lighter and more susceptible to perturbation, might drift inward toward the Sun, while Venus could venture outward. Earth herself might follow a slowly changing spiral, pulled by solar gravity and by the whispers of her siblings' gravitational influence. Imagine the mathematics of this. Every celestial body exerts a pull on every other body, no matter how distant, no matter how small that pull might seem. Over geological timescales, the accumulation of these infinitesimal tugs becomes irresistible. What would become of Mars without Jupiter's stabilizing influence? Would it drift into Earth's orbit, crossing our path with increasing frequency? Or might it spiral inward toward the Sun, eventually colliding with one of its inner siblings or being drawn into the star itself? The truth is, we cannot know with certainty. Planetary dynamics over such vast timescales involve calculations so complex, variables so numerous, that even our most sophisticated computer models can only offer probabilities rather than predictions. And yet the models are consistent in their broad strokes. The inner solar system without Jupiter becomes a system in flux, a region where chaos, in the mathematical sense, gradually overtakes order. Consider, too, the fate of the outer planets. Neptune and Uranus would find themselves unmoored. Without Jupiter's massive gravitational field to constrain them, to hold them in their current orbital shells, these distant worlds would begin a slow migration outward. They might drift past where the asteroid belt once supplied asteroids that occasionally find their way inward. They might encounter the Kuiper Belt, that vast realm of icy bodies at the solar system's periphery, and scatter those ancient objects in all directions. Some would be flung into deep space, escaping the sun's gravity altogether, and drifting eternally through the void between stars. Others would be deflected inward, toward the warmer inner solar system, toward Earth. This is where the cosmic violence would truly emerge, for the Kuiper Belt and the Oort cloud beyond it are reservoirs of comets, ancient, pristine remnants of the solar system's formation, many of them composed largely of water ice and volatile organic compounds. These are the same objects that, when knocked from their distant orbits by passing stars or by gravitational perturbations within our solar system, become the famous comets that occasionally grace our sky with their luminous tails. Without Jupiter's gravitational sentinel to keep most of these bodies at bay, the rate of cometary impacts on the inner planets would increase dramatically. And think of what each such impact represents. Not merely a meteor streaking across the sky, but a potential extinction-level event, a cascade of catastrophe. The history of Earth itself attests to this danger. The extinction of the dinosaurs, 66 million years ago, came at the moment of an asteroid impact, a body perhaps 12 kilometers across that struck the Yucatan Peninsula with energy equivalent to billions of nuclear bombs. The global consequences were immediate and terrible. Dust and ash in the atmosphere blocked the sun, temperatures plummeted, ecosystems collapsed. Scientists now understand that Jupiter's gravitational influence has, across geological time, saved Earth from countless such collisions. The asteroid that struck 66 million years ago was, in a certain sense, an outlaw, a rock that somehow escaped Jupiter's shepherding and managed to find its way into a collision course with our world. Without Jupiter, such outlaws would be far more numerous. One might imagine, then, a scenario playing out over the course of a few 100,000 or million years. The inner solar system, unshepherded and destabilized, would find itself under increasing bombardment. Craters would multiply. The atmosphere would be repeatedly stripped away by impact and outgassing. The oceans would boil and freeze and boil again. Any life that managed to arise would face extinction after extinction, each collision resetting the clock of evolution, preventing the long, patient accumulation of complexity that has allowed life on Earth to flourish for over 4 billion years. We would likely not be here to contemplate Jupiter's absence, because the chain of circumstances necessary for human evolution to occur would have been broken billions of times over. The gravitational vacuum left behind by Jupiter's departure would not announce itself with fanfare or catastrophe, at least not immediately. Instead, it would unfold like a slow tide turning, a patient reorganization of an entire solar system that had been arranged, quite literally, around the presence of this colossal world. In the weeks and months following Jupiter's vanishing, the inner planets would begin their reluctant waltz toward a new configuration, pulled by forces they had never needed to resist before. Consider for a moment the asteroid belt that orbits between Mars and Jupiter. For billions of years, this vast collection of rock and metal has been shaped, contained, and carefully shepherded by Jupiter's immense gravity. The largest asteroids, like Ceres, have been held in a delicate equilibrium, far enough from the Sun to remain relatively cool, yet bound firmly enough not to wander into the paths of the terrestrial planets. But without Jupiter's presence, that invisible leash would gradually lengthen and fray. The asteroids, freed from their celestial guardian, would begin to drift outward and inward, their orbits becoming increasingly unpredictable. Some would venture toward the inner solar system. Over centuries, the probability of collisions would rise significantly, and the probability of some of those objects finding their way toward Earth would rise along with it. This is not to say that the asteroid belt would suddenly transform into a shower of impending doom. The distances involved in space are so vast that even with more asteroids in motion, the chances of any single one striking Earth in the near term would remain statistically small. Yet the timeline stretches into deeper time, and the cumulative effect becomes undeniable. Where Jupiter once acted as a cosmic vacuum cleaner, gravitationally capturing wayward objects and preventing them from reaching the inner planets, there would now be only the Sun's pull and the faint tugs of the remaining planets, Earth and Venus and Mercury, none of which possess the mass to play Jupiter's protective role. The Oort cloud, that spherical halo of icy bodies that surrounds the entire solar system at unimaginable distances, would also feel Jupiter's absence, though the effect would be subtler and require far longer to manifest. Some of the objects within the Oort cloud are held in orbit by the combined gravity of the Sun and Jupiter together. Without Jupiter, certain comets that had been locked in stable, long-period orbits might gradually escape their trajectories. Others might be drawn inward more frequently, increasing the likelihood of what we call long-period comets, those ancient messengers of ice and dust that occasionally pass through the inner solar system and grace our night sky. Think of it as removing one of the pillars holding up a vast, intricate structure. The edifice does not collapse immediately. Instead, the weight redistributes, stresses appear in unexpected places, and the weaknesses that were previously hidden by Jupiter's overwhelming presence would begin to emerge. The solar system would be a less stable place, a less protected place, a place where catastrophe would become not certain, but more probable. And probability, given enough time, becomes destiny. Yet even this tells only part of the story, for we must now turn our attention to what would happen to the planets themselves, and to the world that you inhabit, as the gravity that has shaped their very orbits for 4.5 billion years simply ceased to exist. The cascade of consequences would ripple outward from the first moment of absence, touching systems we rarely think about consciously, yet depend upon every single day. The gravitational absence of Jupiter wouldn't simply mean an emptier sky, it would mean a fundamentally altered geometry of our solar system itself. Consider the asteroids. In that region between Mars and the Sun's warmth lies the asteroid belt, that scattered collection of rocky remnants left behind when our solar system first took shape. For the past 4.5 billion years, Jupiter's gravity has been like an invisible shepherd, constraining these objects within certain boundaries, keeping them in their lanes, so to speak. Without Jupiter's pull, these asteroids would begin to drift and scatter. Some would be flung outward toward the outer solar system entirely, while others, and this is the thought that would have kept ancient astronomers awake, others would find themselves on trajectories that lead inward, toward our orbit, toward Earth. This isn't speculation born of fear alone. Astronomers studying exoplanetary systems, those alien solar systems orbiting distant stars, have observed exactly this phenomenon when massive planets go missing or when systems are disrupted. The asteroid populations become chaotic, unpredictable, dangerous. Over centuries and millennia, this steady rain of incoming asteroids would increase, not dramatically overnight, but with a patient, relentless incrementalism that works against stable civilizations. The impact rate would likely rise by perhaps 3 to 5 times what we currently experience, though the precise number remains uncertain in models. Even that modest-sounding increase would be profound. Right now, Earth is struck by asteroid impacts roughly every million years or so, on average. The larger, truly civilization-altering impacts occur less frequently still, every several million years. But increase that frequency, and the odds begin to shift. What were once rare catastrophes become merely unusual misfortunes. There is something almost peaceful about this realization, in a strange way. The danger isn't immediate. It unfolds across geological time. Civilizations would have millennia to adapt. to develop technologies, to prepare. Yet the mere knowledge of it would change us. The way we plan, the way we think about our future, the way we might organize ourselves as a species. Perhaps we would evolve into a civilization that routinely moves critical infrastructure underground, or develops the capacity to redirect incoming threats. Perhaps we would become more unified in purpose, more focused on long-term survival. But let us not linger too long on the asteroids. They are only one thread in this complex tapestry, because there exists another consideration, one that touches the very heart of how our planet maintains its climate, its stability, its capacity to shelter life in its current forms. The Moon, that faithful companion that has drifted with us since the great impact that formed it, would find itself in a subtly different dance without Jupiter's presence. The Moon's orbit is not simple. It is a three-body problem, a dance between the Earth, the Moon, and the Sun. Jupiter, from its distant throne, has historically exerted just enough gravitational influence to help stabilize this arrangement, to keep it from diverging into chaotic fluctuations. Without Jupiter's steadying hand, the Moon's orbital mechanics would become less predictable over the long term. The tides, those magnificent rhythms that have shaped life on Earth since its earliest emergence, would experience variations that, while perhaps not catastrophic, would be noticeable and strange. The tides themselves are generated by the Moon's gravity, pulling upon our oceans, and to a much smaller degree, by the Sun's as well. These tides have shaped the rhythms of life, the breeding patterns of coral, the migration patterns of salmon, the sleeping cycles of countless creatures evolved to synchronize with lunar cycles. Without Jupiter as a stabilizing influence, even small changes in the Moon's long-term orbital behavior could alter tidal patterns across centuries. Ecosystems finely tuned over millions of years would be forced to adapt to new conditions. There is a meditative quality to contemplating these slow transformations. We are not speaking of apocalypse, but of drift, of gradual, patient change unfolding at the pace of generations, of species, of ages. The Earth would not die, life would not vanish, but the familiar world we know, the one shaped by the specific configuration of our solar system, the one that created the conditions for human civilization to flourish, that world would slowly become something else. And so, as we move deeper into this quiet thought experiment, we arrive at a question that touches something profound about the nature of life itself on Earth. Without Jupiter's protective influence, the bombardment we described would not have simply been a distant, abstract threat to our ancient planet. The very conditions that allowed the chemistry of life to emerge, to settle, to take root in the warm, shallow seas and volcanic vents, would have been fundamentally altered. Consider for a moment the timeline. Life on Earth appears to have begun perhaps 3.7 or 3.8 billion years ago, almost as soon as the planet cooled enough to sustain it. And yet the heavy bombardment continued for hundreds of millions of years after that, which means, in a sense, life was learning to exist in a world that was still under siege. The microorganisms that formed our earliest ancestors were not safe. They were not protected by an atmosphere thick enough to shield them, or by a stable climate, or by the absence of cosmic intruders. They were simply persisting, living in the spaces between catastrophes. And then, slowly, imperceptibly, Jupiter's gravity did its work. The impacts became fewer, the intervals between extinction events grew longer. The climate began to stabilize, and life, that infinitely patient and adaptable force, began to diversify and elaborate. Without Jupiter, we might ask, would life ever have had the chance to do more than merely survive in caves and crevices, in the depths of the ocean where impact shock waves might not reach? There is something almost gentle in contemplating this. Jupiter, massive and distant, working quietly on behalf of a planet it had never touched, a life it could never know. The transition period between the heavy bombardment and our more recent, quieter era of impacts is itself a landscape of uncertainty and possibility. The late heavy bombardment, as scientists call it, seems to have reached its crescendo around 3.8 billion years ago, though some researchers propose models in which the timing was rather different, in which the Nice model, named for the French city where it was developed, suggests that the giant planets themselves migrated from their original positions, reshuffling the entire architecture of the solar system. In this scenario, Jupiter did not always sit where it sits now, and perhaps, in some versions of events, Jupiter's current position is itself the result of complex gravitational dances that redirected countless planetesimals, turning them away from the inner worlds or hurling them outward into the cold edges of space. If Jupiter had never migrated, if it had never achieved its current orbit, then the entire shape of impact history would have been different. The architecture of our world would have reflected a different configuration of the heavens. This is where our thought experiment begins to blend seamlessly with the actual history of the solar system, because we are not truly imagining something impossible, we are imagining something that might have happened but didn't. As the impacts thinned and slowed, something else was happening on Earth. The young planet was developing its own defenses. The bombardment had heated the surface repeatedly, sterilizing it, driving away any chemical compounds that might have been fragile or unstable. And yet, with each resetting of the cosmic clock, new minerals formed. New rock faces were exposed. Water, which had been locked in meteorites and delivered in abundance by the very impacts that threatened life, accumulated in the early oceans. And within this harsh, energetic environment, chemistry became biology. The first self-replicating molecules emerged, whether they were RNA or some other arrangement of chemistry that we have yet to discover in the fossil record, something that could take in energy, metabolize it, and create copies of itself. This is where the story of life and the story of Jupiter's gravitational influence become inseparably woven together. Because without the reduction in impacts, without the gradual clearing of the solar system's debris, the energy would have remained destructive rather than generative. Too many impacts sterilize, too few, and perhaps the chemical complexity required for life never fully develops. There is, almost certainly, a Goldilocks zone for planetary bombardment. Not too hot, not too cold, but just right for the emergence of living things. The irony, if one might call it that, is that we are here because of Jupiter, and yet we are here in spite of Jupiter's early neighbors. The planetary system that Jupiter inherited when it first formed was far more crowded than the one we see today. There were likely protoplanets, or planetary embryos, in orbits that would later be swept clean. Jupiter's gravity would have either accelerated these bodies toward the inner solar system or flung them outward into the cold reaches beyond Neptune. Most would have been destroyed in collisions, or ejected into interstellar space. And the impacts that resulted, the collisions that seemed so destructive from the perspective of early Earth, were in fact the necessary mechanism by which the solar system stabilized itself. Without those collisions, without Jupiter shepherding the chaos, we might have inherited a solar system even more crowded and unpredictable than the one we almost inherited. And life, in such a system, might never have found the stability to develop beyond the simplest chemical reactions. So we arrive at this thought. The impacts that nearly ended life before it began were themselves a consequence of Jupiter's influence, an inevitable part of the process by which Jupiter made life possible. The orbital dance that once seemed immutable would begin to fracture almost imperceptibly at first. Within weeks, the gravitational void left by Jupiter's sudden absence would ripple outward through the solar system like stones cast into still water, each one creating rings that touched distant shores. Saturn, that slow and stately giant, would find itself untethered from centuries of gravitational partnership. The two planets had existed in a kind of cosmic waltz, each influencing the other's trajectory through the invisible architecture of gravity itself. Without Jupiter's steady pull, Saturn would slowly drift into a new orbital path, one that might carry it closer to the Sun, or perhaps farther away, depending on where exactly in its own cycle it happened to be when its partner vanished. But it is not merely the outer planets that would feel this disruption. The inner solar system, seemingly distant from such cosmic rearrangement, would experience changes that might seem subtle at first, but would compound with each passing year and century. Mars, that rusty world that has always occupied a particular zone between the terrestrial worlds and the outer giants, would find its own orbit subtly modified. The perturbations that Jupiter had been applying to Mars for billions of years, small nudges that prevented certain catastrophic possibilities, would gradually fade away. We might wonder whether Mars would drift inward toward Venus and Mercury, or whether it would simply settle into a slightly different orbital velocity that would create new resonances with the inner planets. The asteroid belt would undergo perhaps one of the most dramatic transformations. Remember that Jupiter had been serving, in a manner of speaking, as the great shepherd of the solar system. Its gravity wells had been capturing countless fragments that might otherwise have streamed inward toward the terrestrial worlds. The NICE model, which scientists developed over recent decades to explain the early architecture of our solar system, suggests that Jupiter actually migrated significantly during the first few million years of the Sun's life, stirring and scattering asteroids across vast distances. Without Jupiter present now, the belt would lose its gravitational guardian. Over time, measured in millions of years, asteroids that had been kept relatively stable in their current orbits would begin to drift. Some might fall inward, pulled by the Sun's gravity on slightly altered trajectories. Others might be ejected outward, flung into the cold reaches beyond Neptune. The asteroid belt itself might gradually disperse, becoming a thinner, more spread-out collection of fragments rather than the relatively concentrated zone we know today. And those inward-drifting asteroids would eventually pose a new and persistent threat to the inner solar system, to Venus, to Mercury, and most significantly to the world that would suddenly find itself without its ancient shield. Earth's situation in this scenario becomes the heart of our contemplation. For all of our recorded history, all of human civilization, all of the billions of years that life has existed on this planet, Jupiter has been overhead in the cosmic sense, a massive guardian whose gravity well has been deflecting or capturing the vast majority of comets and asteroids that might otherwise strike us. The Grand Tack hypothesis, which some planetary scientists favor, even suggests that Jupiter migrated inward early in the solar system's history and then back outward again, and in doing so, it may have actually delivered the water and organic compounds that became the foundation for life on Earth. Yet that same powerful protector would also be, without it, conspicuously absent from the role it has played since. The loss of Jupiter would mean that Earth would gradually become a world more exposed to impact. Not immediately and not catastrophically at first, but increasingly over millions of years, the probability of major asteroid strikes would rise. We can calculate this with relative confidence because astronomers have modeled such scenarios, studying what happens when you remove major gravitational influences from celestial systems. The impacts would come less frequently than they did in the early solar system, when bombardment was nearly continuous, yet far more frequently than Earth has experienced in recent geological time. What does that mean for a world like ours? It means that extinction events caused by impact, which we thought were perhaps 20 million year or 100 million year phenomena in our current cosmic arrangement, might become century-spanning concerns or events that occur every few million years rather than every 50 or 100 million. Picture the oceans in the weeks and months that would follow such a cataclysm, as the gravitational wounds slowly deepened. The tides, already diminished to mere whispers, would continue their strange metamorphosis, but now something far stranger would begin to unfold in the waters themselves. The great ocean currents that have circled our planet for millennia, those massive conveyor belts that carry heat from the equator toward the poles and cold water back again, would begin to falter in ways that oceanographers can barely predict, let alone describe with certainty. These currents are not driven solely by tides, you understand, but by differences in water temperature and salinity, by the very weight and pressure of water stacking upon itself. Yet the loss of the moon's gravitational pull would diminish the mixing of surface and deep waters, the churning and cycling that has become fundamental to how our oceans breathe. The Atlantic meridional overturning circulation, that grand river within the ocean that brings warm tropical water northward and sends cold polar water back south, would weaken considerably. Some researchers speculate it might slow by half or more, though others suggest it could collapse entirely. And in that collapse lies a particular kind of peril. The warmth that currently moderates Europe's climate, that keeps the British Isles and Scandinavia far warmer than their latitude alone would suggest, would gradually diminish. Not all at once, mind you. The planet's thermal inertia is immense. The oceans have capacity to hold and release heat across decades and centuries. But over generations, the thermal picture of the North Atlantic would transform, and with it, the climate patterns that billions of people depend upon. And as the oceans changed, so too would the atmosphere respond. The interaction between ocean and air is one of the most intimate and consequential relationships on Earth. Warmth rises from the water into the sky, moisture ascends and condenses, patterns of wind and pressure cascade outward in waves of cause and effect. A reduction in tidal mixing would mean less upwelling of nutrient-rich water in certain regions, and where nutrients fail, the tiny plants of the ocean, the diatoms and coccolithophores and countless species of phytoplankton, begin to fade. These creatures form the foundation of marine life, and their decline would ripple upward through every scale of predator and prey. But let us consider another layer still, one that exists in the realm of subtlety and slow cascades. The Earth's magnetic field, that invisible shield that deflects the solar wind and protects our atmosphere from being slowly stripped away into space, is generated deep within the planet's iron core. The mechanisms that create it remain partly mysterious, involving the convection of molten metal and the planet's rotation. There is ongoing scientific debate about whether the moon exerts any meaningful influence on Earth's magnetic field generation. But what is becoming clearer is that the moon's presence has shaped certain aspects of our planet's behavior over extremely long timescales. Its gravitational presence has stabilized Earth's axial tilt, keeping it at roughly 23.5 degrees. This tilt is what gives us our seasons, and though we tend to think of it as fixed, it actually wobbles slightly, and without the moon's gravitational stabilization, this wobble would grow. Over periods of millions of years, a more volatile axial tilt would lead to wild swings in seasonal intensity. Sometimes the tilt would increase toward 40 degrees or more. Other times, it might decrease substantially. What does this mean in practical terms? Imagine summers in the continental interiors becoming scorching beyond present experience, while winters plunge to depths that would freeze the atmosphere itself. Imagine the global climate system swinging between extremes with a regularity and amplitude that no modern organism has been shaped by evolution to survive. The protective regularities that we now take for granted, the gentle cycling of the seasons, the predictable monsoons, the return of familiar weather patterns, all of this would become alien and hostile. And yet, in the immediate time frame we have been considering, in the first years and decades after the moon's disappearance, the axial tilt would only begin its slow drift away from stability. The changes would be gradual enough that human instruments might struggle to detect them within a single lifetime. But sensors and records, year after year, would begin to show subtle shifts. The axis would start its long wobble, like a top that has received a gentle nudge and is beginning to precess in larger and larger circles. And all the while, life on Earth would be adapting, or failing to adapt, to the cascade of physical changes already underway. The biosphere, in its own way, is a kind of current too, flowing and shifting according to the conditions that surround it. What does it mean for an entire evolutionary system to face such a transformation? Life on Earth has weathered extinction events before, has survived impacts and volcanic winters and periods of anoxia that would seem unimaginably harsh to the delicate creatures we see today. Yet each of those events unfolded across timescales of thousands or millions of years, allowing some organisms to evolve, some to migrate, some to find refuge in isolated pockets where conditions remained survivable. The disappearance of the moon would be different in its character, not a sudden, violent disruption, but rather a slow, fundamental rewriting of the rules that govern habitability itself. As we move deeper into this quiet thought experiment, we arrive at a threshold that requires us to consider something that astronomers call the Late Heavy Bombardment, a period in the early solar system when cosmic violence was not the exception, but almost the rule. To understand what might happen without Jupiter, we must first understand what Jupiter has already prevented and what it continues to prevent each and every day through its patient, invisible guardianship of the inner solar system. Picture this ancient solar system, if you will. The sun has just ignited. Planets are still settling into their orbits. Countless planetesimals, fragments of rock and ice ranging from the size of mountains to the size of continents, still drift through the spaces between the young worlds. In this chaotic nursery, collisions are constant. Worlds reshape themselves through impact. Material transfers from one orbit to another, and in this maelstrom, Jupiter emerges as something like a cosmic vacuum cleaner, though not in the way you might initially imagine. The common misconception is that Jupiter acts as a shield, deflecting all dangerous objects away from Earth and the inner planets. This is partially true, but the reality is far more complex and far more interesting. Jupiter's gravity is indeed powerful enough to capture or eject many bodies that might otherwise threaten the terrestrial worlds. Yet Jupiter also destabilizes orbits. It pulls and tugs at objects in ways that can send them either outward into the void or inward toward the Sun. The mathematical dance between Jupiter's mass and the orbital mechanics of smaller bodies is one of exquisite sensitivity. What we know from studying our own solar system's history and from simulating other solar systems in supercomputer models is that without a Jupiter-like body in the outer system, the inner solar system would have remained a far more violent place for far longer. The rate of large impacts on Earth, impacts that we know from the geological record actually did occur, but perhaps with greater frequency, would have been substantially higher. Think of it not as complete protection, but as a statistical thinning of the bombardment, a reduction in the probability of extinction-level events during the critical window when life was first beginning to establish itself. Now, this raises a profound and quieting thought. If Jupiter had never formed, or if Jupiter had somehow been ejected from the solar system in those first chaotic millions of years, then the asteroid impacts on the early Earth would have been more frequent and more severe. The surface of our planet would have remained molten, or at least extremely hostile, for a longer period. This window, the window during which life might have begun, would have been narrower, or perhaps closed entirely. Does this mean that without Jupiter, Earth would never have developed life? Not necessarily. Life is remarkably persistent and resourceful. But it does mean that the conditions would have been far harsher, the timeline extended, the probability reduced. And probability, when stretched across billions of years, is everything. Consider too what we understand from the study of exoplanetary systems, those distant worlds orbiting other stars that we have only begun to observe in detail over the past few decades. Astronomers have discovered that many star systems do not have a Jupiter. These systems have only small inner planets, or they have large planets orbiting very close to their parent star. In these systems, the inner regions remain, it seems, more chaotic. The planets are less stable in their orbits. There is evidence, though still being refined, that habitable zones in such systems are narrower and perhaps less conducive to the long-term stability that complex life requires. What this gently suggests, and we must be careful here to distinguish between what we know and what we reasonably infer, is that the presence of a large outer planet acts as an orbital stabilizer for the entire system. Jupiter, by its mass and position, creates what physicists call a structure to the solar system. It carves out zones of relative stability. Without it, those zones would blur and shift and become less reliable. The terrestrial planets would not simply drift out of the habitable zone, rather, their orbits would fluctuate more, their stability compromised. This is not to say that Jupiter is the sole reason life exists on Earth. Many factors were necessary: the particular mass of the Sun, the position of Earth at the right distance, the presence of a moon to stabilize Earth's tilt, the chemistry of our planet, the emergence of liquid water. Each of these is essential. But Jupiter is perhaps best understood as a supporting actor in this extraordinary cosmic drama, not the lead, but integral to the whole production. What Jupiter does, fundamentally, is grant time. It grants the stability necessary for the chemical and biological processes to unfold without constant interruption from catastrophic impacts. It allows oceans to form and remain liquid. It allows complex molecules to assemble. It allows the first self-replicating systems to emerge and evolve without being repeatedly reset by extinction-level bombardment. Without Jupiter, time would have remained compressed. The window would have been narrower. The probability of life arising would have been lower, though perhaps not zero. And this quiet realization that our existence is tied not just to the characteristics of our own planet, but to the gravitational influence of a massive world hundreds of millions of miles away, invites us to consider the profound interconnectedness of this solar system we inhabit. The ancient Greeks called Jupiter the king of gods, and they were onto something profound without quite knowing why. When you stand in the presence of something so immensely larger than yourself, something so gravitationally dominant that entire worlds orbit within its sphere of influence, you begin to understand why early astronomers felt compelled to name it after their supreme deity. But what they saw through those first telescopes, and what their naked eyes could observe in the night sky, was only a fraction of Jupiter's true power in this solar system, a power that extends not just through space, but backward through deep time itself. Consider for a moment the nature of planetary migration. In the earliest chapters of our solar system's history, those first few million years when our sun was still surrounded by a vast disk of stellar dust and planetary embryos, Jupiter was not always where it is now. The evidence suggests, with increasingly strong support from both observation and simulation, that Jupiter formed much closer to the Sun, perhaps orbiting in a region where today only asteroid fragments and memories exist. And then, in a process that must have taken less time than you might imagine, Jupiter began to move. It drifted inward, then outward again, in a slow gravitational waltz with Saturn and the other forming planets. This migration, which we call the Grand Tack hypothesis, fundamentally shaped the architecture of everything that came after. This inward journey had catastrophic consequences for whatever worlds were forming in its path. Planetary embryos were scattered. Some were ejected from the solar system entirely, sent spinning into the void between stars. Others were ground together through violent collisions that released energy beyond comprehension. And yet, here is the paradox that makes this moment in our solar system's history so delicate to contemplate. If Jupiter had not migrated inward, if it had not stirred this cosmic soup, the Earth itself might never have formed at all. The delivery mechanisms for water and organic compounds, those precious building blocks that would eventually lead to life, depended partly on the gravitational disruptions that Jupiter created as it moved. Now imagine Jupiter not simply migrating, but vanishing entirely during this critical early epoch. The stability that would eventually emerge would be profoundly different. Without Jupiter's mass anchoring the inner solar system, without its gravitational dominance constraining the motions of the other terrestrial planets, the formation process of Venus, Earth, and Mars would unfold along entirely different pathways. Mercury, that small and scorched world closest to the Sun, might have formed into something utterly unrecognizable. The Earth itself, already fragile in its early years, buffeted by impacts and subject to the gravitational pulls of every other body in the planetary system, might have been cast into a completely different orbit, or might never have accumulated sufficient mass to become the world we know. But let us imagine Jupiter's disappearance at a different moment in time. Suppose our solar system had already settled into something approximating its current configuration. The terrestrial planets had coalesced. The Earth was already ancient by some measures, perhaps 2 billion years old, already bearing the weight of a much simpler biosphere. What would happen then? The immediate gravitational consequence would ripple outward like a stone dropped into still water. The planets orbiting closer to the Sun would begin, very slowly, to experience less overall gravitational constraint. Earth would not suddenly spiral into the Sun. The Sun's own gravity would still dominate Earth's orbit, but the perturbations caused by Venus and Mercury, which are ordinarily somewhat damped by Jupiter's enormous mass, would become more pronounced. Over millions of years, the orbital paths of these worlds would begin to drift in ways that are difficult to predict precisely, for orbital mechanics at this scale involves a kind of chaos, where tiny initial variations produce vastly different outcomes. There is something almost dreamlike about contemplating this, is there not? A world existing in a state of dynamic equilibrium, where one great presence organizes the motion of everything else, and then suddenly that presence is gone. The system does not collapse immediately, it does not end, but it begins, in that moment, to forget the pattern it had learned to hold. Consider also what Jupiter does for the outer solar system. Neptune and Uranus, those distant, ice-bound worlds that receive only a faint whisper of the Sun's warmth, orbit in a region that has been shaped entirely by Jupiter's gravitational shepherding. Jupiter is, in essence, the fence that keeps the outer solar system from wandering. It maintains a kind of boundary, a gravitational membrane. Beyond this boundary lies the Kuiper Belt, that vast region of icy bodies and dwarf planets, and further still, the Oort cloud, that theoretical shell of icy objects that some astronomers believe surrounds the entire solar system at a distance so vast that the Sun itself becomes merely a bright star among bright stars. If Jupiter were to vanish, the gravitational structure that has held this distant realm in relative order would immediately begin to dissolve. Neptune and Uranus would begin to drift. Some models suggest they might move outward, driven by interactions with the remaining asteroids and icy bodies. Others suggest they might move inward. The precise outcome depends on details that we cannot fully know without running the simulation, and even then, the chaos inherent in gravitational systems means that small uncertainties mushroom into vast unknowns. What we can say with some confidence is this: the Kuiper Belt would become fundamentally unstable. Those hundreds of thousands of icy bodies, currently held in a relatively well-defined region of space by the combined gravitational influence of the giant planets, would begin to scatter. Some would be ejected from the solar system entirely, becoming wandering worlds, orphaned planetesimals traveling through the interstellar void. Others would be flung inward, toward the sun and toward the region where the rocky planets orbit. This inward migration of icy bodies is perhaps the most immediately dangerous consequence of Jupiter's disappearance for any civilization that might inhabit the Earth. In our actual solar system, Jupiter acts as a kind of gravitational shield. Its enormous mass creates something that astronomers sometimes call a cosmic vacuum cleaner. The way Jupiter's gravity works, it tends to pull inward the very asteroids and comets that might otherwise threaten the inner planets. Some of this material falls into Jupiter itself, some is ejected entirely from the solar system. But the net effect is that Earth is protected. The rate at which potentially dangerous asteroids and comets strike our world is much lower than it would be otherwise. Think about what this means as you drift further towards sleep, allowing your mind to rest in this imagined scenario. Without Jupiter, this protective influence would vanish. The inner solar system would experience a dramatic increase in the frequency and severity of impacts. Small asteroids that are now too small to notice would pass close to Earth. Larger ones would potentially strike. The geological record of our actual Earth shows evidence of such bombardment, particularly in the earliest eons of the solar system's history. But we live in a relatively quiet time now, a time when major impacts are rare. Remove Jupiter, and that quiet would end. And as we turn our attention now to the delicate matter of orbital dynamics, that intricate choreography of gravity and momentum that keeps our solar system in its present familiar arrangement, we begin to see just how profoundly Jupiter's absence would alter not only where things move, but why. They move the way they do. You see, the planets are not simply scattered across empty space like beads on a string. Each one pulls on every other, exerting a gravitational influence that, while invisible to our eyes, guides their paths through the darkness in ways both obvious and surprisingly subtle. In the early years following Jupiter's hypothetical vanishing, and let us imagine this happened gradually enough that the solar system didn't tear itself apart in the first instant, the inner planets would begin to behave in ways that would seem almost erratic to an observer watching from Earth. Mercury, for instance, that swift and elusive world closest to the Sun, would find its orbit changing noticeably. Mercury has always been pulled, very gently, by every other planet in the system, but Jupiter's immense gravitational reach has always been one of the dominant forces shaping its path. Without that steady guiding hand, Mercury's orbit would become more elongated over time, more irregular. Its journey around the Sun would take on what astronomers call a higher eccentricity. It would swing in closer to the Sun at one point in its orbit and drift farther out at another, in patterns different from what we observe today. Venus would experience something similar, though her situation is complicated by the fact that she orbits closer to the Sun than Mercury does, in a region where the Sun's gravity dominates above all else. Still, across the vast spans of geological time, millions of years, hundreds of millions of years, the redistribution of gravitational influences would be measurable. Venus might settle into slightly different orbital patterns. Her year, the time it takes to complete one full circuit around the Sun, might shift by mere hours or days over the course of centuries, but it would shift nonetheless. These changes would be glacially slow to our perception, but persistent, inexorable. And then there is the question of what astronomers call resonances, those remarkable alignments that occur when two orbiting bodies interact in such a way that their orbital periods bear a simple mathematical relationship to one another. Earth and Venus, for example, come into a rough 5 to 8 resonance with one another, that is to say, roughly 5 times in the time it takes Venus to orbit the Sun. Earth does so 8 times. These resonances can either stabilize orbits, keeping them in orderly paths, or they can destabilize them over time if certain conditions are met. And Jupiter, in its massive way, has been a kind of invisible governor of these relationships, maintaining certain configurations and preventing others from developing. Without Jupiter's influence, might new resonances form? Might some of the delicate balances that have held for billions of years begin to shift? Astronomers cannot say with absolute certainty, but the models suggest that yes, over very long periods indeed, we might see the emergence of orbital patterns quite unlike anything in our solar system's present age. Consider too the question of what might happen to the Hilda family of asteroids, a group of rocky bodies in the outer region of the main asteroid belt that are held in their current orbits largely by, you have guessed correctly by now, Jupiter's gravitational pull. The Hildas engage in what's called a 3-to-2 resonance with Jupiter. For every 2 times Jupiter orbits the Sun, these asteroids complete 3 orbits. This resonance has kept them in a region where they neither spiral inward toward the Sun nor scatter outward into the void. Remove Jupiter, and the Hildas would lose this organizing principle. Many would drift, their orbits becoming unpredictable. Some might wander inward, others might scatter outward into the regions beyond, becoming part of the scattered disk, or eventually drifting out toward the interstellar medium itself, lost to the solar system forever. The same would be true, though perhaps to an even more dramatic degree, for the Trojan asteroids, those curious bodies that share Jupiter's orbit, clustered in 2 great swarms, one ahead of Jupiter and one behind. These Trojans are gravitationally trapped in what are called Lagrange points, equilibrium positions in the orbital plane where the gravitational forces of Jupiter and the Sun balance in such a way that an object placed there can remain there indefinitely, orbiting in stable harmony with the larger bodies. With Jupiter gone, those Lagrange points would cease to exist. The Trojans would suddenly find themselves in a different gravitational landscape altogether, and they would disperse. Some might collide with one another, others would be flung toward the Sun or outward into the void. Within a few million years, the great swarms of Jupiter Trojans, vast assemblies of thousands of bodies, some of them as large as small moons, would be scattered and dissipated, a cloud of orphaned asteroids adrift in space. And here we arrive at a quieter but no less profound consequence, the loss of these asteroids, and especially the loss of the resources they represent. Some of those Trojan asteroids contain rich deposits of metals and water ice. In our present solar system, they remain at the very edge of what our species might one day be able to reach and harvest. But if they were dispersed, scattered into the darkness, they would become effectively inaccessible, scattered too far, moving in too many different directions. A civilization seeking resources in the outer solar system would find them suddenly much harder to find, much harder to gather. And for the Earth, for our world as a potential home for future generations, the loss of Jupiter as an anchor for these faraway populations might mean one fewer source of supply in an era when resources beyond our world become vital to human survival. But let us move deeper still into the chains of consequence, into the realms where gravity and chemistry and the slow dance of planetary formation begin to interweave in ways that reveal how profoundly interconnected all things are in the solar system. And so we arrive at a curious threshold in this imagined world without Jupiter, a moment where the very chemistry of life itself begins to shift beneath our feet, though we might not notice it at first. The ocean's composition, you see, would gradually transform over centuries and millennia, and this transformation carries within it a whisper of consequence that touches almost every living thing. You understand that the oceans are not static bodies of water, but rather dynamic systems constantly exchanging elements with the atmosphere, the rocks beneath, and the creatures that inhabit them. Jupiter's absence would set off a chain of reactions that begins with something almost invisible to us: changes in atmospheric chemistry, driven partly by the altered radiation environment and partly by the slow shift in how Earth's magnetosphere behaves without the protection Jupiter once provided. The upper atmosphere would receive more ultraviolet radiation, more cosmic rays penetrating deeper than before. These energetic particles don't simply pass through the air unnoticed. They ionize molecules, break apart chemical bonds, and create entirely new compounds that would have been rare or non-existent in Jupiter's shadow. Over very long timescales, and here we step into the territory of informed speculation paired with what we know of planetary chemistry, the composition of seawater would drift. Trace elements that arrive from space, cosmic dust, meteoritic material, would accumulate differently. The balance of salts and minerals, built up over billions of years to a precise concentration, would begin, ever so slowly, to shift towards something unfamiliar. The ocean that had maintained roughly the same chemical character since early in Earth's history would develop a faintly different signature, as if someone had very gradually altered the recipe of a salt that has been unchanged since time immemorial. And what of life itself, dwelling in these slowly transforming waters? This is where our story becomes less a tale of dramatic catastrophe and more one of profound transformation, unfolding at the pace of generations stacked upon generations. The creatures of the sea, particularly the smallest ones, the diatoms and coccolithophores that form the foundation of oceanic food webs, live in exquisite equilibrium with their chemical environment. A fish does not simply survive in salt water through passive acceptance. Its cells are actively maintaining an internal balance, constantly working to keep its internal environment different from the outside world. Organisms have evolved over millions of years to thrive within a very specific range of conditions. When those conditions shift, even gradually, something must give. Some species would find themselves struggling against currents they did not evolve to resist. Others, perhaps, would discover unforeseen advantages in this altered world. The slow change in ocean chemistry might favor different organisms entirely, ones whose physiology could tolerate or even exploit the new salinity regime, the new mineral concentrations, the new pH balance of waters that are inching toward conditions their ancestors never knew. The coral reefs, those cathedral structures built from the calcium carbonate skeletons of countless polyps, would find themselves in particularly delicate circumstances. Corals are extraordinarily sensitive to the chemistry of the water surrounding them. They require not just the right temperature, but the right concentration of dissolved minerals. They need specific conditions to build their skeletons, and they need their symbiotic algae partners to thrive. A world without Jupiter's protection brings with it more ultraviolet light, penetrating deeper into the water column than before. And in the shallow tropical waters where coral lives, this increased radiation would stress the algae that gives coral its color and much of its food. Combine this with slowly shifting ocean chemistry, and the coral realm faces a compounding pressure, a squeeze from multiple directions at once. Imagine then a reef system attempting to persist in a world of accumulated stresses, not the sudden bleaching event that modern climate change might trigger, but something slower, more insidious, more like a slow erosion of the conditions that make that ecosystem possible. Some corals might adapt, or migration might shuffle the composition of reef communities, but others might simply fade, leaving behind limestone skeletons in waters that have become, by the most subtle of degrees, a little less welcoming to their kind. The microscopic plankton that drift in the sunlit waters would face their own reckoning with this transformed environment. Diatoms with their glass-like silicate shells, copepods with their delicate structures, the entire constellation of zooplankton and phytoplankton that exists at the threshold where light meets the sea. All of them would be responding to an ocean that is minutely, but persistently, different than the one their species knew before. Some lineages would diversify and flourish in new niches. Others would contract, their ranges shrinking as their preferred conditions became harder to find. And yet, here we must pause and acknowledge the profound resilience of life itself. Life on Earth has, across its vast history, survived far more dramatic changes than a slow drift in ocean chemistry. Species and ecosystems possess remarkable flexibility within certain bounds. They adapt, they migrate, they diversify in response to shifting circumstances. The question is not whether life would persist in this altered world, it almost certainly would, but rather what form that life would take and what would be lost in the transition. The irony, perhaps, is that this slowness of change would be both mercy and torture. A sudden catastrophe can trigger rapid evolution, clear selection pressures, obvious winners and losers. But a slow transformation, unfolding across thousands of years, might go almost unnoticed by the organisms experiencing it, until one day, a species that thrived for millions of years simply fails to reproduce as successfully as it once did, and its descendants become fewer and fewer still, until silence falls where complexity once lived. That is how extinction often works, not with a bang, but with a long, patient fading away, one generation less viable than the last, until the thread is broken and no longer mends. What we glimpse here, in this chemistry of consequence, is that Jupiter's absence would ripple not just through climate and geology and the sky itself, but through the very molecular foundation upon which Earth's biological narrative is written. The script would not change entirely, perhaps, but it would be rewritten page by page, word by word, letter by letter, in a language only life itself can truly read. The absence of Jupiter would ripple through the solar system in ways that touch even the distant edges where we rarely imagine consequences reaching. Consider the Kuiper Belt, that vast ring of icy bodies orbiting far beyond Neptune's realm, where thousands of small worlds drift in the dark cold beyond the sun's warmth. Jupiter's gravitational presence, even across such tremendous distances, acts as a kind of gentle shepherd for these distant objects. It nudges them, constrains their wanderings, prevents them from spiraling into chaotic orbits that might one day send them hurtling toward the inner planets. Without Jupiter's presence, the Kuiper Belt would not suddenly vanish. Instead, it would become profoundly unstable, released from the gravitational bonds that have held it in relative order for billions of years. The objects there, some the size of small moons, others mere fragments of ancient rock and ice, would begin to drift. Their orbits would slowly expand or contract. Some would spiral outward into the realm of interstellar space, while others might begin a long glacial journey toward the warming regions closer to the sun. This process would unfold across millions of years, not suddenly, but with inexorable certainty. Imagine the patience of deep time itself, watching as these distant travelers began their new journeys into the void. The asteroid belt, too, would experience this cosmic freedom from constraint. The larger bodies there, Ceres and the other dwarf planets, would find their orbits changing, sometimes moving closer to Mars, sometimes drifting outward. The finer dust and smaller rocks would scatter more rapidly, some crossing paths with the inner planets. Perhaps the most profound consequence would come in the form of comets. These icy messengers, formed in the outer reaches of the solar system, would lose the orbital guidance that Jupiter provided. Some would fall inward toward the sun at an increased rate, their trajectories less predictable, their arrivals less orderly than they have been throughout Earth's history. The great impacts that shaped the early solar system, the late heavy bombardment that scarred the moon and may have brought water to Earth, all of that ancient violence occurred in a solar system still ruled by Jupiter's ancient gravity. Now, without that governing force, we must ask ourselves, would such bombardments begin again, not once more, but regularly, continuously, as the newly freed objects from the Kuiper Belt and the asteroid belt began their long spiral inward? Would the inner planets face a return to that dangerous era, when impacts were routine and extinction was always merely a matter of waiting long enough? The timescales are difficult to grasp, because the solar system operates on rhythms that dwarf human understanding. A cascade that takes 1,000,000 years seems instantaneous to the cosmos, yet represents more time than humans have walked upon the Earth. The drift of a distant ice body might require 3,000,000 years to bring it from the quiet reaches of the Kuiper Belt to a collision course with Mars or Venus. But eventually, inevitably, the mathematics of orbital mechanics would win. The solar system's delicate architecture, maintained by Jupiter's presence, would crumble into a state of higher chaos and greater danger. Life on Earth, as we have discussed, would not survive the immediate consequences of Jupiter's disappearance. But even if it somehow did, if we imagine a world where the climate stabilized and the magnetic field held and the atmosphere remained breathable, life would face a new and eternal threat from above. The sky itself would become less predictable. The night sky, which for billions of years has shown us the steady progression of stars and the regular returns of comets, would become a more hazardous realm. The probability of Earth's collision with a sizable object would increase significantly. And here lies one of the great, humbling truths of existence on our world. We live under the protection of forces so vast and so distant that we rarely perceive them. Jupiter orbits the Sun more than 5 times farther from us than we do. It is a world we visit only with our instruments and our imagination. Yet its presence has been the difference between a solar system stable enough to nurture life for billions of years and one that remains perpetually volatile and dangerous. The planets that neighbor us, Mars and Venus, would also find themselves changed by Jupiter's absence. Mars, smallest and most vulnerable of the terrestrial worlds, would experience perturbations in its orbit. Venus, locked in its thick atmosphere and hellish heat, would drift into slightly different patterns around the Sun. Neither would become more habitable, but both would become more unpredictable. The careful orbits that have defined our solar system since its formation would unwind, not explosively, but with the steady, relentless patience of gravity over deep time. This is perhaps the most subtle of all the consequences we might imagine, yet in some ways the most profound: the loss of predictability itself. For billions of years, the solar system has been a place of order and pattern. The planets keep their distances, the seasons return on schedule, the tides follow the moon. Life has organized itself around these rhythms and regularities. Remove Jupiter, and you remove a crucial pillar of that order. What remains is still a solar system, still governed by physics and mathematics, but one that is fundamentally less stable, less predictable, less hospitable to the flourishing of life. In the context of cosmic history, the existence of Jupiter in our solar system represents an extraordinary stroke of fortune. Some scientists have speculated that Jupiter-like planets around distant stars may be essential to the development of life on their smaller, neighboring worlds. The concept is sometimes called the Jupiter barrier or the Jupiter defense, the idea that large planets in the outer reaches of a system act as gravitational shields, protecting the smaller inner worlds from bombardment by the wandering bodies of the outer system. Could it be that countless worlds throughout the universe lack life not because they failed in some biological or chemical way, but simply because they lacked a Jupiter, because they lacked that great sentinel hanging in their outer darkness, shepherding the dangerous wanderers, maintaining the peace and stability that life requires to emerge and flourish? What emerges from this deeper examination is perhaps the most unsettling possibility of all. one that scientists have only begun to seriously consider in the last few decades. Without Jupiter's protective gravity, the inner solar system would not simply experience a gradual increase in impacts. Instead, it would face a fundamental reorganization of its entire architecture, a reshuffling so profound that the very concept of orbital stability would require redefinition. Imagine, if you will, the asteroid belt freed from its keeper's gravitational leash. For billions of years, Jupiter's pull has served as a kind of cosmic boundary, a fence that prevents the wandering bodies beyond its orbit from drifting too freely into the territories of Mercury, Venus, Earth, and Mars. But what happens when that fence is suddenly removed? The asteroids would not simply drift forward in a disorganized cloud. Instead, they would experience what orbital mechanics calls a resonance cascade, a phenomenon where the gravitational influences of the remaining planets begin to interact with these freed bodies in increasingly complex patterns. The Sun's gravity would still dominate, of course, but without Jupiter's massive stabilizing influence, the Sun's pull would interact with the remaining planets in ways that create what we might think of as highways of danger. Certain orbital paths would become exponentially more likely for asteroids to follow. Others would become surprisingly stable. It would be rather like removing a traffic director from an intersection and watching the flow of vehicles reorganize according to entirely different rules. Some researchers have modeled scenarios where, within perhaps a few million years following Jupiter's disappearance, the asteroid belt would actually fragment into multiple distinct populations. Some asteroids would spiral inward toward the inner solar system. Some would be ejected outward into the Oort cloud, that distant sphere of icy bodies that surrounds the entire solar system. And some, perhaps most troublingly, would remain in the belt but with dramatically altered orbital characteristics, creating what astronomers call a more chaotic state, where precision prediction becomes nearly impossible. This reorganization would have profound consequences for the long-term habitability of Earth. Let us think about a timescale measured not in centuries or even millennia, but in millions of years. The asteroid impacts that we discussed earlier would not be confined to a single catastrophic bombardment followed by relative peace. Rather, they would likely be distributed across an extended period, perhaps spanning tens of millions of years. The frequency might not be constant either. There could be periods of relative quiet, followed by epochs where impacts would cluster more densely. For a world already stressed by the loss of its orbital guardian, such prolonged asteroid bombardment would create challenges that extend far beyond the physical damage. Each impact would inject enormous quantities of material into the upper atmosphere. Each one would create dust clouds that would reduce sunlight reaching the surface. And while a single impact might last months or even a few years in terms of its climatic effects, a series of impacts spread across millions of years would create a kind of perpetual twilight, a prolonged cooling that might push the entire biosphere toward the edge of what it can endure. There is something deeply reflective about considering such a scenario from the perspective of evolutionary biology. Life on Earth has survived many challenges throughout its history. It has weathered ice ages and volcanic supereruptions. It has adapted to dramatic shifts in atmospheric composition and ocean chemistry. But all of these survived ordeals occurred within the context of a relatively stable orbital environment. The presence of Jupiter, though we rarely think about it, has meant that the Earth has enjoyed what we might call a cosmic insurance policy, a kind of protection that has allowed life to evolve and flourish without constantly facing the threat of sudden, violent interruption. Without that protection, would evolution itself have proceeded differently? Would intelligence have arisen on Earth if our planet had been subject to more frequent and devastating impacts throughout its history? These questions venture into pure speculation, certainly, but they hint at something profound about our place in the cosmos. We exist in a particular arrangement of celestial bodies, a configuration that has made our existence possible. Not only has Jupiter protected us from impacts, but in a very real sense, Jupiter's presence has shaped the entire context in which life could develop on our world. And here we must pause to consider something that scientists are still working to fully understand. There is emerging evidence that suggests Jupiter itself may not have always been where it is today. Some models propose that in the early history of the solar system, Jupiter may have migrated from an inner orbit outward to its current position. Other models suggest that Saturn may have been involved in a dramatic gravitational dance with Jupiter, pulling it outward through the solar system. If these migration scenarios are correct, then the solar system has experienced periods in its past that were somewhat analogous to what we are imagining now. Periods where Jupiter was not in its current position and the inner solar system experienced different orbital dynamics. What those early periods might have been like remains genuinely uncertain. The geological record on Earth is too ancient to preserve clear evidence of the impact rates that might have occurred during the early solar system. The asteroids that might have impacted us billions of years ago have long since been buried or eroded away. But there are clues in the arrangement of craters on the Moon, in the composition of meteorites, and in the subtle orbital characteristics of the planets themselves. These hints suggest that there may have been times in the solar system's history when the bombardment was indeed more severe than it is today. If such times did exist, then Jupiter's eventual arrival and establishment in its current orbit would have represented a kind of cosmic salvation for the inner solar system, a transition from chaos to order, from uncertainty to relative stability. The question then becomes almost poetic. In losing Jupiter, would Earth be returning to a state that once existed, merely replaying an ancient chapter of planetary history? Or would the absence of Jupiter create something truly unprecedented, a situation unlike anything the solar system has ever experienced? And so, in this imagined solar system without Jupiter, we arrive at perhaps the most profound of all the cascading consequences, the question of life itself, and whether Earth as we know it would have ever been possible at all. Because what we're beginning to understand, as we follow the threads of this thought experiment deeper and deeper, is that Jupiter's role in our existence is not merely peripheral or secondary. It is foundational in ways that our ancestors could never have grasped, ways that only become visible when we attempt to remove it entirely. Consider, for a moment, the sheer improbability of what happened in our actual history 4.5 billion years ago, when our solar system was still a roiling chaos of colliding asteroids and protoplanetary disks. Something rather remarkable occurred. A massive planet, Jupiter itself, migrated inward from its original formation zone, then outward again, in a dance so intricate and finely balanced that astronomers still debate its exact choreography. And during those migrations, something crucial happened. The gravitational wake of Jupiter's movement sculpted the architecture of the inner solar system. It cleared certain orbits of excess debris, while leaving others abundantly populated. It stabilized the zones where terrestrial planets could form, all while preventing certain planetary embryos from ever coalescing into existence. Think of it as a cosmic gardener, pruning away branches that might have grown, nurturing others toward maturity. Without that gardener working in those early billions of years, the inner solar system would have evolved along a path we can barely imagine. There might have been more terrestrial planets. There might have been fewer. They might have had different orbits, different masses, different compositions. The zone where Earth eventually formed might have been far too crowded, far too violent for the specific sequence of collisions that brought our planet into being. And here lies the truly vertiginous thought. Earth itself might never have formed. Or if something did form where Earth formed, it might have been a radically different world. Without Jupiter's careful gravitational choreography, without its centuries-long waltz through the early solar system, the particular combination of matter and energy and gravitational influence that assembled our home planet might have scattered to the stellar winds. The building blocks might have assembled differently. The ratios of iron and rock might have been altered. The trajectory that led, eventually, to the moon-forming giant impact, that cataclysmic collision between the proto-Earth and a Mars-sized object called Theia, might never have occurred at all. Because here's something that keeps many planetary scientists awake at night. Though they might not admit it readily, the Moon might not have formed without Jupiter's stabilizing presence. And without the Moon, Earth would be a fundamentally different place. The Moon gives us our stable axial tilt. It gives us our tides. It gradually slows our rotation and lengthens our days. Over billions of years, the Moon's influence has shaped the rhythm of life itself, the tidal cycles that governed when early organisms could expose themselves to the sun and the air, the lunar cycles that synchronized with biological processes and reproductive cycles. A world without Jupiter is, by that strange chain of causation, a world that might never have possessed a moon. And a world without a moon is a world where the emergence of complex life becomes far more difficult, perhaps impossible. The tilt of Earth's rotational axis, the very thing that gives us seasons, is stabilized by the Moon's presence. Without it, Earth's axial tilt could oscillate wildly over geological timescales, swinging perhaps from near 0 degrees, which would mean no seasons and a frozen equator, to extreme angles, which would mean scorching poles and unpredictable, violent climate swings. A world with such unstable seasons would be a world hostile to the evolution of complex multicellular life. Plants and animals require some degree of predictability in their environment. They need to be able to anticipate winter and summer, to evolve the strategies, dormancy, migration, hibernation, that allow them to survive seasonal extremes. A world wobbling chaotically on its axis would be a world where that kind of biological planning becomes impossible. It is true, we should note, that there is speculation here, educated speculation, grounded in rigorous simulation and observation, but speculation nonetheless. Planetary scientists cannot run the experiment. They cannot rewind the cosmic clock and watch what happens without Jupiter, because they are trapped, as we all are, within the single instance of reality that actually occurred. What they can do is build mathematical models. They can simulate the gravitational interactions of thousands upon thousands of particles in a disk of primordial dust and gas, allowing Jupiter to exist or removing it, and observing what configurations of planets emerge. And these simulations, repeated countless times with slight variations, consistently show that a solar system without Jupiter produces a radically different outcome in the inner reaches. More planets, fewer planets, or planets in entirely different orbits. The variations are many, but a system that produces an Earth and a Moon orbiting in the configuration that actually exists, that outcome becomes far less likely. Some simulations never produce it at all, and so we confront a dizzying possibility that life on Earth, and perhaps life anywhere in this solar system, is not inevitable. It is contingent. It depends upon a long chain of improbable events, each one necessary for the next. Remove Jupiter from the equation, that single massive planet, that gravitational architect of the inner solar system, and the entire chain might collapse. The planetary configurations that led to Earth might never have assembled. Or if something did assemble, it would be something else entirely, a world with a different tilt, a different climate, a different moon or no moon at all. And in such a world, the emergence of humanity, of any intelligence that could contemplate the cosmos and wonder about its own existence, becomes exponentially less probable. This is not to say that life itself requires Jupiter, exactly. In other solar systems, around other stars, complex life might emerge under entirely different circumstances, with entirely different architectures of planets and gravitational balances. But in this solar system, our solar system, the one we inhabit, the existence of every plant and animal and human being stands on the foundation that Jupiter provided. We are, in a real and measurable sense, Jupiter's children. The cascade of consequences would continue to unfold across centuries and millennia, shifting the nature of life itself in ways both subtle and profound. Without Jupiter's gravitational anchor steadying the solar system, the remaining planets would gradually begin to drift into new orbital patterns, some of these changes occurring so slowly that they might escape notice across the span of a single human lifetime. Yet across the deep time of geological epochs, the reshaping would become undeniable. Mars, now freed from Jupiter's distant but persistent gravitational influence, would begin a slow orbital migration. The red planet might drift either closer to the Sun or further away, the direction depending on the specific perturbations left behind by Jupiter's absence. If Mars were to move inward, toward warmer regions of space, its thin atmosphere might experience a faint revival of energy, more solar heat reaching its surface, more potential for chemical reactions in its soil. Or if Mars drifted outward instead, it would become even more of a frozen world than it already is, a deep frozen monument to what might have been. Venus, that hellish neighbor of Earth, would also feel the change. The gravitational architecture that once kept Venus in its current orbit, locked in that slow retrograde rotation that makes a day on Venus longer than its year, would be altered. Venus might wobble in its orbital path, might tilt differently on its axis, and these seemingly small adjustments could have cascading effects on its already extreme greenhouse atmosphere. The planet would continue to be hostile to life, perhaps more so than ever, but it would be a differently hostile world. The asteroid belt, that scattered ring of rocky remnants between Mars and where Jupiter once orbited, would experience the most dramatic transformation of all. Without Jupiter's immense gravity to shepherd and shape it, the asteroid belt would begin to disperse. Some asteroids would gradually spiral inward toward the inner solar system, drawn by the gravitational wells of the terrestrial planets. Others would be flung outward into the outer reaches of space, escaping the Sun's embrace entirely. Within a few million years, the asteroid belt would unravel. Where once there was a defined region with a certain density of objects, there would instead be scattered pieces drifting through much larger volumes of space. This outward drift of asteroids would pose new dangers to the inner planets. Earth, in particular, would find itself in a slightly more hazardous neighborhood. The frequency of large asteroid impacts on our world would likely increase, at least for a time, not immediately, not suddenly, but across millions of years, the collision rate would rise. The geological record would show more large impact craters, more evidence of sudden catastrophic events. Each impact would send dust high into the atmosphere. Each would disrupt the climate in ways that would tax whatever biosphere existed at that time. And here we must pause and consider what sort of life would even exist on Earth by this point, so far removed from Jupiter's departure. The life that now covers our world, all the vast diversity of creatures and plants and microorganisms, evolved within the protective embrace of Jupiter's gravitational umbrella. Life became what it is, in some sense, because of Jupiter's presence. Remove that presence in our thought experiment, and the evolutionary pathways branch differently. The animals that now exist might never have evolved. The plants might have taken different forms. The whole tree of life would have redrawn itself according to different rules, following different survival pressures. Perhaps in this timeline where Jupiter is gone, life would be more resilient to impacts, having evolved under more frequent bombardment, or perhaps life would be more fragile, having had fewer stable millions of years to establish deep roots and complex relationships. The uncertainty here is profound, almost vertiginous when you sit with it. We cannot know what form life would take, because we cannot fully know what forms life took on Earth, precisely because Jupiter was here, guiding our cosmic neighborhood, holding back chaos. Consider also the longer orbital dance between Earth and other planets without Jupiter present. Mercury would maintain its swift path around the Sun, barely changed, its tiny mass irrelevant to the larger gravitational mathematics. But Saturn, that other giant that orbits even further from the Sun than Jupiter once did, would notice the difference. The gravitational tango that Jupiter and Saturn performed, these two massive bodies distant from each other, would be lost. Saturn would orbit more freely, less constrained, and the ripples from this change would propagate outward. The great comets that occasionally venture into the inner solar system from the outer reaches, those ghostly visitors that appear in Earth's sky, bearing tails of ice and dust, would follow different paths without Jupiter there. Some of these icy bodies would miss us entirely, passing through where Earth once was, but finding nothing there. Others might venture even closer than they would have with Jupiter present. The rhythm of celestial visitations would change. What does it mean to imagine a world, or rather, a solar system, without the guardian that shaped it? It is, in a way, to confront the fragility of existence, the particular nature of luck that we inhabit. Not just luck, really, but a kind of cosmic attunement, a set of circumstances that allowed complexity to flourish and persist long enough for consciousness to emerge. Jupiter, in its slow, patient orbit around the Sun, has been one of the crucial instruments in this symphony. Without it, the music plays differently, the whole composition transformed. In the wake of this imagined catastrophe, what remains is not despair, but a kind of humbling recognition. Jupiter, in its silent orbit, has been performing a role so vast and so essential that we rarely pause to acknowledge it. It pulls, it guards, it deflects, and in doing so, it permits the delicate persistence of life on a small blue world we call home. To contemplate a solar system without Jupiter is to understand, at last, what we possess. We live beneath a guardian whose gravity wells draw in the debris of creation, whose immense shadow falls across the night sky as both warning and promise. The asteroid that might have ended our world is instead scattered into the cosmic dark, its trajectory bent by forces we cannot see, but which shape every sunrise and every breath we take. How strange, how profoundly strange, that our survival rests upon the movements of something so distant that we perceive it only as a bright point among points of light. And yet this thought need not trouble us as we drift toward sleep, for Jupiter remains exactly as it has been for 4.5 billion years. Its mass has not diminished, its orbit has not shifted. The cosmic machinery that brought us into being and sustains us still continues in its perfect, measured way. To imagine its absence was to know its presence more intimately than we ever could have otherwise. In those stretches of the night when you might glimpse Jupiter yourself, that steady, patient gleam in the winter sky or the summer darkness, you might feel something that earlier generations felt when they first noticed it moving against the background of stars. A sense of continuity, a gentle assurance that we are held, quite literally, by forces larger than ourselves, by mathematics and matter and time unfolding across the vastness of space. The planet will remain there long after we have fallen asleep and long after we have woken. It will remain through the turning of seasons, through generations yet unborn, through ages that we cannot imagine. There is a certain peace in surrendering to this knowledge, not passivity, but acceptance. The universe is vast and often indifferent, yes, but it is also orderly, bound by laws that work in our favor more often than against us. Jupiter is one of those laws made visible. It is nature's protection written in gravity and stone. As the night deepens around you, as your thoughts grow gentler and slower, consider this: you are alive in an era of knowledge and wonder. You can know what would have become of the world if Jupiter had never formed, or if it had been knocked from its orbit eons ago. You can understand the mechanisms of your own survival. And understanding changes everything. It transforms fear into fascination, uncertainty into a deeper kind of gratitude. The asteroids still drift through space, countless and ancient. Some carry water, some carry the chemistry of life itself. They tumble through the solar system on trajectories that were settled when Jupiter was young, when the inner planets were still coalescing and finding their places. And because Jupiter guided them, because its gravity created a boundary between the violence of the outer system and the fragile nursery of the inner worlds, we were born, you were born, against odds so astronomical that they seem almost impossible to express. You exist. This is not a burden to carry into sleep, but a gentleness to wrap around yourself. You are part of a story that extends backward through billions of years and forward toward an unwritten future. You are made of atoms that have traveled through supernovas and asteroid collisions and the patient darkness of interstellar space. And you are here, now, thinking about Jupiter, wondering what might have been, suspended in that beautiful state between wakefulness and dreams, where all possibilities seem equally real and equally strange. The solar system that exists is not the only one that might have existed, but it is the one that did. It is the one that brought you here. In that plain fact lies something profound. Not certainty, never certainty, but a kind of rightness. A sense that despite the violence and randomness that attended your creation, despite the near misses and the close calls, and the moments when a slightly different physics might have erased you from all possible worlds, you arrived. You were meant to, perhaps, or perhaps it was only chance, but you arrived nonetheless, and now you are here, aware and wondering, held safely beneath the guardian sky. As your eyes grow heavier and your breathing grows slower and deeper, let yourself rest in that knowledge. The night above you is not empty but full of Jupiter's presence, full of the ancient story of how you came to be, full of the quiet mathematics that keeps the worlds in their orbits. That story does not need your attention or your worry. It proceeds on its own, vast and patient and eternal, whether you are awake or sleeping. The solar system will continue. Jupiter will continue its ancient dance around the sun. The asteroids will follow their courses. And you, for now, can let go of imagining what might have been and simply allow yourself to exist in what is. That is gift enough. That is more than enough.